This is going to be the first in several videos on 10.3 polar functions. I want to start with a review just kind of what we talked about way back at the beginning of this year, and which we did a little bit of in your AP prep days. So I want to talk about different curves, how to put it onto your calculator, and then also what you should be able to do by hand. So if you want to grab your calculator, and you may need to pause this video at times to actually do it on your calculator, but you can turn it on and make sure when you go to mode that you're in radians as always, and that you're going to go down to polar mode. So in polar mode, when you hit the Y equals button, what you're going to see is a bunch of R1 equals, R2 equals, and so on. So you can input several different polar graphs simultaneously if you want. So first, let's take a look at just R equals 2. And what we want to do, because the aspect ratio on your calculator is 3 to 2, that is, there's 3 times as many pixels horizontally as there is vertically. If you want something that should look like a circle to really look like a circle, you need to make your x-min and max be 1.5 times the difference between your y-min and y-max. So we're going to see that R equals 2 is a circle of radius 2. So to make it really look like a circle, you want to choose your x-min and x-max to go from -3 to +3, and your y-min and y-max to go from -2 to +2. When you do that, you're also going to see that you're going to get an orientation with these graphs, much like we see with parametrics. So in the world of polars, the origin is also known as the pole, and we'll kind of flow back and forth between that. We'll call it probably equally as often the origin or the pole, and likewise the positive x-axis or polar axis are going to be interchangeable. So this is what it looks like at theta equals 0 radians, and if I had my hands and I could show you in class, I would try to sweep it going counterclockwise, in that it's going to look like what I would say Doppler radar. If you've ever seen that, like on the evening news or on the Weather Channel or something, it kind of sweeps around counterclockwise. And that's how we're going to graph in polars. So what you're seeing when you do this on your calculator is it's doing it very fast, but at angle 0, it's going to plot a point that is an R value of 2, that is a distance from the pole or from the origin of 2, and then it's going to work its way through different angles as it goes up to pi over 2, and all the way to pi, and down to 3 pi over 2, and so on. And so you're going to get this sweeping, you're going to get a direction that it is going counterclockwise. So you're going to get a circle of radius 2, and it has what we would call an orientation, a direction. So if you, and I neglected to mention, but you could say theta is going to go from 0 to 2 pi. And because 0 is going to be this angle, and of course one full trip around will take us to 2 pi. Now, if you graph R equals -2, you're going to get the same circle of radius 2, but you're going to see a different orientation. So at the angle of 0, where it starts, it's going to start here at an angle of 0, but the R value negative is going to shoot it through the pole, and the first point that you're going to see plotted is going to be over here, and we will always label our coordinates in rectangular. In AP, you would label that as -2, 0, which ironically enough on the first one would be the same in both polar or rectangular, because in polar we would go r comma theta, which is what that is, and in rectangular we would go xy, which that also is, but that only happens on the first one. Then as we sweep through these different angles, we're getting an R value of -2, which means the point that gets plotted actually goes through the pole into quadrant 3, and so you're going to get this curve, and it's still going to be that same circle of radius 2, but this one you will see starts at a different place because it's going to start at -2, 0, whereas our blue one, the R equals +2, started at 2, 0, and it too is going to be oriented in the counterclockwise direction. Now, another kind of polar equation, kind of a sort of simple one, but not so simple on your calculator, is if you have something like theta equals pi/6, then you can't input that into your calculator in polar mode, just like you can't graph in rectangular mode something like x equals 2. There's just no good way to do that. But what this means is we're going along the angle pi/6. So if you imagine here is an angle of pi/6, and oops, I kind of goofed there. So at the angle of pi/6, we're going to let R be anything that wants because there is no restriction on R. So if R is 0, we'll get this point and a +1 and 2 and all of the positives. But then also when we get negative values for R, we're going to shoot through the pole and we're going to get something that extends down into quadrant 3. And so theta equals pi/6 is just this line through the origin with a slope whatever the tangent of pi/6 is. Okay, so what I'd like you to do is to first get some comfort and practice and review doing this on your calculator, and then I'm going to go on and we'll talk about what we need to be able to do by hand. So if you graph something like R equals 2 times the sine of 6 theta, this is going to be what we call a rose curve. And again, when you're setting up your window, you can see that the largest that a sine can ever be is 1, and that's going to get multiplied by 2. So the largest that this value of R can ever be is going to be 2. So you can, at least in your mind, visualize that the largest our graph will be, the furthest away from the pole our graph is ever going to be, is a circle of radius 2. So you would set your x-min and x-max. Again, you would go from -3 to 3 on the x-min and x-max, -2 to 2 on the y-min and y-max. What we will see is a rose curve is anything in the form a sine n theta, or it could be R equals a sine of n, cosine rather, of n theta. So the n, if n is odd, then that will be the number of petals. And if the n is even, then we will have 2n petals. And so you can see here, because the n is 6, you're going to get a rose curve with 12 petals, which is pretty cool, but I'm not going to try to graph that here. You can take a look at it on your graphing calculator, though. Now, you can also try on your graphing calculator R equals 1 minus 2 cosine theta. This is from the family of curves that are known as lemmasones. And so that's anytime we have something in the form R equals A, either A plus or minus. I'm just going to say plus and say that B could be negative as well. And then sine theta, or it could be in the form R equals A plus B cosine theta. So there's kind of four different kinds of limasones, and one of those, when we'll do this by hand in a little bit. When A is equal to B, and I'm not worried about the plus or minus. That's just going to be an orientation. That's not going to affect which kind of curve it is. When A is equal to B, we're going to get a cardioid. You may remember that. When the B is bigger than A, like you see in this one that you're going to do on your graphing calculator, then it's going to be what we call a looped limacone, or a limacone with an inner loop, either way. And if the A is bigger than the B, then we will get a dimpled or dented limacone. Either of those is interchangeable. And if the A is more than twice what B is, then we get the most boring one, which is just a convex limacone. That is, it's just going to look like a big egg. So you can go ahead and graph that one on your calculator and see what it looks like. You should see a looped limacone. I'm going to go to a new page here, and you can see if you can graph on your calculator r equals 4 sine of theta. You might think of that, which would be it would be an okay way of thinking of it, as a rose curve with one petal. So that is, it's going to look like a circle. You need to be a little careful when, sometimes I think it helps, like when you have your R equals on your calculator, when you look to the left side there, if you hit enter until you get this 0 to show up, it will trace it as you do the curve. It may be surprising, you'll find when you do this one that you're going to get a circle, but it's going to trace that circle actually twice. So if you put that circle on it, you're going to see that it actually traces over that circle twice if your theta goes from 0 to 2 pi. So that's going to be something that's important as we do the calculus of this, because we're going to eventually be talking about things like arc length or area of slices here. And so it's important to know, to make sure that we're only tracing over a curve one time if we're looking for an arc length, or being careful what our area is as we graph these. So it's going to be important at least to have an understanding of what's going on there graphically. So the last kind, and I think these are kind of boring, but supposedly these come up. I'm not sure if I've seen one on an AP exam, but if you get something of the form r squared equals a squared, either cosine of 2 theta, or if you get r squared equals a squared times the sine of 2 theta. Anything in that form is known as a lemniscate. And I don't think they're all that interesting. To enter this into your calculator is a little bit of a challenge, because you have to take the square root of it. So you would have to enter into your calculator, R1 is equal to, and then you'll get the square root of that for cosine of 2 theta. And then into R2, you could either go negative the same thing, or if you want to practice getting your skills on your calculator, you could go negative, and then if you go to the variables, to polar, and then you can put it in as R1. At any rate, when you do this, it'll trace out, in this case, when you have the r squared equals a cosine of 2 theta, you're going to get something that's going to look like either a propeller blade or a figure 8, whichever way you want to call it. It's going to have a radius that is the square root of that a. So in our case, that's going to be 2. And you're going to get something then that's going to look sort of like, they're a little wider loops than like a rose curve. So these petals or loops or propeller blades are a little wider than they would be in the case of a rose curve. So an r squared equals cosine is going to look something like that, and r squared equals the sine 2 theta is going to just have a different orientation. it's going to have the propeller blades going along the line theta equals pi over 4, and so it would look still something like these figure eights or propeller blades. But that is going to be what a lemniscate that has a sign in it's going to look like. And that's essentially it for lemniscates, so I don't think they're terribly interesting, but supposedly we need to know them. So let's talk about some things that you should be able to do by hand. So I'm going to say be able to graph by hand. And I don't imagine that you're actually going to have to do this on an AP exam. I don't remember this ever coming up where you really have to do it, and certainly not on one that you're going to do because it's going to be all on the computer. But I think it helps with your understanding, so I will ask you to do it if I ever have a chance to give you a test again. So we need to be able to do, as we said, Rose curves. We need to be able to graph by hand limasones, and we need to be able to graph by hand lemniscates. So I'm going to post on there a file, a review of polar graphing, and it has an explanation of how to do these, again, in written form if you want to look at it, and it has some examples that you can do. So if you feel like you need more practice, that would be a way to do it, or maybe also when we zoom in. So let me do at least one example of each of these. So let's say our first one is going to be, we'll do a Rose curve, r equals 2 sine of 3 theta. So we can see that the 2 is going to tell us that the furthest away from the pole this graph will ever be is going to be 2. So I'm going to just graph kind of a dotted circle so that I have a boundary and I know what the furthest points are going to go from there. Now, the ends of the petals are going to be on that circle. So I'm going to first find the end of the first petal. And to do that, I want to know where is sine 3 theta first equal to 1, because that's where sine is going to be its biggest. So the biggest sine can be is 1, and we want to know for what angle theta is that going to be 1. So we know that the sine of pi over 2 is equal to 1, so that means we want to find a value of theta that when we multiply it by 3 will equal pi over 2, and of course that's going to be pi over 6. So we will go to what we estimate to be an angle of pi over 6. So I'm going to call, there's our theta equals pi over 6, and I'm going to just put a point on the circle of radius at that point right there. That's the end of our first petal. Then we know the spacing between petals is going to be, they're going to be evenly spaced. So the spacing between petals is going to be 2 pi, which is the full circle, divided by, we know there's going to be 3 petals because that n is odd. So that means that our second petal is going to be from the end of our first petal, pi over 6. We're going to add to that a 2 pi over 3 to get to the next petal. So getting a common denominator, we're going to get that to be 5 pi over 6. So that means if we go to an angle of 5 pi over 6, then we are going to plot the end of our second petal, and I'll do that in green right there. In a similar fashion, we'll find the third petal by adding another 2 pi over 3 to that last petal, the end of that last petal, which was 5 pi over 6. And so that's going to be 9 pi over 6, or if we believe in reducing, would be 3 pi over 2. So when we go to 3 pi over 2, then we're going to put an end of a petal right there. And the way to graph this is to start at the end of the first petal. I'm going to go look across the circle and 180 degrees, and then I'm going to move counterclockwise to the end of that next petal. So starting at the first petal and aiming for this petal, I'm going to draw an arc that connects those going through the pole. So it's going to look something like that. And that will kind of give you an idea of sort of what it's going to look like sort of when the calculator does it. And you'll also get, I think, a better shape on those, so it's not as fat as a pedal as you would get, say, in a lemniscate. We'll do that again. I'll look at the end of this second pedal. I'm going to look across the circle 180 degrees, turn my attention counterclockwise to the next one, and I'm going to connect that end of that pedal to the end of the next one going through the pole. And likewise, I'm going to go through the pole to connect to that first one. And there is our rose curve with 3 petals. Let's try another one. Let's do, we'll do a limacone. So we'll do, in this case, R is equal to 2 minus 2 sine theta. So a little different strategy. This is a limacone. And hopefully we'll recognize what it is. We'll learn to recognize what it is. But if we don't, you can kind of get it anyway. It'll kind of evolve in the course of graphing it. So I'm going to wait to name it. You may know what it is already. But we're always, with the limacone, we're going to plot the angle 0, pi over 2, all the quadrants, the quadrantal angles. That is, we're going to plot the points right on the quadrant boundaries. So we're going to plug in theta equals 0, pi over 2 pi, 3 pi over 2, and then we're going to find the value of r at those angles, and then we're going to plot those on our xy axis, and then we're going to think like Doppler radar and try to connect those. So at angle 0, sine of 0 is 0, and so 2 times 0 is 0, and that's going to make r equal to 2. So at the angle 0, I'm going to go out 2, and I'm going to put a point on the curve there. At pi over 2, sine of pi over 2 is 1, and so 2 minus 2 is 0. So I'm going to plot a point on the angle pi over 2. I'm going to plot that at 0, which is the pole or the origin. At pi, sine is 0 again, and so that's going to give me an r value of 2 again. So our angle pi is coming out this way. I'm going to come on that angle out 2 from the pole and plot that point. And finally, at 3 pi over 2, sine is negative 1, so that's going to be 2 minus 2 times negative 1 is going to be an r value of 4. So on the angle of 3 pi over 2, I'm going to come out 1, 2, 3, 4, and I'm going to plot that point right there. Now, as we connect these, we want to imagine that we're going to start at this point right here, our beginning point, and then thinking like Doppler radar, as we sweep through there, we are going to go from an r value of 2 to an r value of 0. So it's going to kind of make its way back into here. And then likewise, as we go from pi over 2 to pi, as we're coming out this way, different angles, our r value is going to go back from 0 to 2, so it's going to gradually get bigger, and we're going to come out to here. Then continuing down into quadrant 3, it's going to go from 2 all the way to 4. And as we go into quadrant 4, from 3 pi over 2 to 2 pi, we're going to get back to there, and it's a little shaky looking, but that kind of is supposed to be suggestive of a heart, and so as you might have recognized, that we will call a cardioid. If I can get my pen back, it's going to be a cardioid. Okay, let's do another one. And so I'm going to graph here our lemniscate. So r squared is equal to, we'll say, 4 sine of 2 theta. This is going to be not a whole lot to this, I don't think. So we know that when we take the square root of both sides, that our radius is going to be 2. So I'm going to go to 2 and put a dotted circle in here to just be kind of a boundary or a guide for the way we graph this. Now we know that a sine is going to get its biggest value. It will be its largest at pi over 2. So we will say 2 theta is equal to pi over 2. This is where r will be the largest. So we're going to kind of get that boundary. And so when you divide, you're going to get theta equals pi over 4. So that means we're going to, on the angle pi over 4, there's our angle pi over 4. Whoops. Pi over 4. Then we are going to have a point on our curve there. And basically from there, that's all we really need to know. We know its shape is going to be this propeller-like or figure 8 shape. We know that it's going to extend down here, and so we just kind of draw that kind of wide, open, wider than a petals on a rose curve, and that's essentially all we do for a lemniscate. And so I don't know that these are all that interesting. Okay, like I said, I'm gonna put a worksheet on Canvas that you can work some more practice problems if you like, and then I'll have some more videos where we're going to start talking about the calculus of polars.